Imagine a universe teeming with mysteries, where silent travelers from distant stars weave through the cosmos, carrying secrets of alien worlds. The discovery of interstellar objects, celestial wanderers that originate beyond our solar system, has ignited a spark of wonder in humanity's quest to understand the universe. These enigmatic visitors, like Oumuamua, 2I/Borisov, and the newly discovered C 2025 N1A TLAS, are not just rocks or comets. They are cosmic messengers, offering glimpses into the formation of distant planetary systems and the potential origins of life itself. Buckle up for an exhilarating journey through the stars as we unravel the stories of these interstellar pioneers, explore their profound implications, and ponder the future of cosmic exploration. This is a tale of science, mystery, and the boundless curiosity that drives us to look beyond our own backyard. On October 19, 2017, the night sky over Hawaii became the stage for a historic moment in astronomy. The University of Hawaii's Pan-STARRS 1 telescope, funded by NASA's Near-Earth Object Observations program, was diligently scanning the heavens for asteroids and comets that might pose a threat to Earth. That evening, it detected something extraordinary: a faint, fast-moving object approximately 33 million kilometers away, traveling at a staggering 314,000 kilometers per hour, over 4 times the average speed of solar system objects. Initially cataloged as 1I/2017 U1, this object defied expectations. It lacked the telltale coma or tail of a comet, suggesting it might be an asteroid, yet it exhibited a slight acceleration, a trait more akin to comets. This puzzling behavior sparked a global scientific frenzy. Astronomers quickly realized they had stumbled upon something unprecedented: the first confirmed interstellar object to visit our solar system. Named Oumuamua, meaning a messenger from afar arriving first in Hawaiian, this cosmic visitor was unlike anything seen before. Its discovery was a testament to the power of modern telescopes like Pan-STARRS 1, which had been designed to detect near-Earth objects, but proved capable of spotting far rarer interstellar travelers. NASA confirmed that Oumuamua originated from another star system, a groundbreaking revelation that opened a new chapter in our understanding of the cosmos. While astronomers estimate that ISOs pass through our solar system roughly once a year, their small size and faintness make them nearly impossible to detect, until Oumuamua changed the game. What made Oumuamua so captivating was its bizarre appearance and behavior. Observations from the European Southern Observatory's Very Large Telescope, VLT, in Chile, led by astronomer Karen Meech at the University of Hawaii's Institute for Astronomy, revealed that Oumuamua was not your typical space rock. Its brightness fluctuated dramatically every 7 hours, indicating it was tumbling end over end, a motion suggesting an elongated, irregular shape. Scientists estimated Oumuamua to be 100 to 1,000 meters long, but only about 35 meters wide, roughly 10 times longer than it was wide. Picture a cosmic cigar, or perhaps a flattened, spinning pancake hurtling through space. This shape was unlike the chunky, boulder-like asteroids and comets native to our solar system, which typically have more balanced dimensions. Further observations revealed Oumuamua's surface to be reddish, a hue reminiscent of objects in the outer solar system, likely caused by millions of years of cosmic ray bombardment. Its composition appeared to be dense, dry, and primarily made of rock and metals, with no signs of the icy outgassing typical of comets. Yet, its slight acceleration as it moved away from the sun hinted at something more complex. Was it a comet without a visible tail, an asteroid with an unusual propulsion mechanism, or something else entirely? The debate raged on, with scientists worldwide scrambling to study this fleeting visitor before it vanished into the interstellar void. The discovery of Oumuamua sparked a flurry of hypotheses, each more intriguing than the last. Initially, scientists were divided into 2 camps: those who believed it was a comet and those who argued it was an asteroid. Comets, composed of ice and dust, often accelerate as they approach the sun due to outgassing, where solar heat vaporizes their ices, creating a visible coma or tail. Asteroids, being rocky, lack this behavior. Oumuamua's acceleration suggested comet-like properties, but its lack of a coma or tail challenged this classification. This paradox fueled intense debate and led to some extraordinary theories. In 2018, astrophysicist Roman Rafikov from the University of Cambridge proposed a radical idea. Oumuamua might be a fragment from a dying star. When a star collapses into a white dwarf, its immense gravitational forces can shred nearby asteroids, moons, or even planets, sending debris hurtling across the galaxy. Could Oumuamua be one such shard, a relic of a cataclysmic event in a distant star system? This theory painted a haunting picture of cosmic destruction, with Oumuamua as a survivor of a stellar apocalypse. Some scientists even speculated that our own sun, destined to become a white dwarf in billions of years, might one day scatter similar fragments into the cosmos. Perhaps the most tantalizing hypothesis came from Harvard astronomer Abraham Loeb in September 2018. Loeb suggested that Oumuamua could be a technological relic, an extraterrestrial spacecraft or solar sail, abandoned and drifting after millions of years. A solar sail, propelled by the pressure of starlight, would require an extremely thin structure with a low mass-to-area ratio, which could explain Oumuamua's acceleration. Loeb estimated it might be as thin as 3 millimeters, though this conflicted with observational data suggesting a more robust structure. While the idea of an alien artifact captured the public's imagination, it also underscored the challenge of distinguishing natural phenomena from potential signs of intelligent life. To test this hypothesis, a team led by Emilio Enriquez from UC Berkeley conducted observations using the Robert C. Byrd Green Bank Telescope, GBT, as part of the Breakthrough Listen initiative. They searched for radio signals from Oumuamua, which could indicate a technological origin. Despite covering the object's full rotational phase with high sensitivity, no signals were detected, suggesting Oumuamua was not an active alien probe. Yet the absence of evidence was not evidence of absence, and the possibility of an ancient derelict spacecraft remained a topic of fascination. The mystery of Oumuamua persisted until March 22, 2023, when a study published in Nature by Jennifer B. Bergner of UC Berkeley and Daryl Z. Seligman of Cornell University offered a compelling explanation. They proposed that Oumuamua was an icy planetesimal, a small body of rock and ice formed in a distant protoplanetary disk. During its interstellar journey, cosmic rays from supernovae bombarded its surface, converting about 1/3 of its water ice into molecular hydrogen trapped within the ice. As Oumuamua approached the sun, the heat triggered the release of this hydrogen, acting as a natural propellant and explaining the observed acceleration without a visible coma. Unlike heavier gases like carbon monoxide or carbon dioxide, hydrogen's low mass meant it left no detectable tail. This model elegantly resolved the comet versus asteroid debate, suggesting Oumuamua was a comet-like object with a unique history. "We do not need to invoke extraordinary explanations," Bergner noted, emphasizing that natural processes could account for Oumuamua's behavior. This discovery not only clarified Oumuamua's nature, but also highlighted the potential for interstellar comets to carry the building blocks of life across the galaxy, raising profound questions about the origins of life on Earth. Just 2 years after Oumuamua's discovery, another interstellar object captivated the astronomical community. On August 30, 2019, amateur astronomer Gennady Borisov, using a self-built telescope at his Margo Observatory in Crimea, spotted a faint object moving in an unusual direction. Unlike main-belt asteroids, this object's trajectory suggested it was not bound to our solar system. Borisov reported it to the Minor Planet Center, which confirmed its interstellar nature, naming it 2I/Borisov, the second known interstellar object. Unlike Oumuamua, 2I/Borisov was unmistakably a comet. Observations by the Hubble Space Telescope on October 12, 2019, revealed a prominent coma and tail, hallmarks of cometary activity. Whereas Oumuamua appeared to be a rock, Borisov is really active, more like a normal comet, said David Jewett of UCLA, leader of the Hubble observation team. Its nucleus, estimated to be 1.4 to 6.6 kilometers in diameter, was surrounded by a fuzzy coma caused by the sublimation of ices as it approached the Sun. This activity made 2I/Borisov a stark contrast to Oumuamua's barren appearance. Traveling at 110,000 miles per hour on a hyperbolic orbit, 2I/Borisov was not captured by the Sun's gravity. It zoomed past Jupiter by mid-2020 and exited the solar system, destined never to return. Its brief visit provided a rare opportunity to study an interstellar comet's composition. Spectra revealed the presence of water vapor, cyanogen Cn, and diatomic carbon C2, compounds typical of solar system comets. The fact that the comet's properties appear to be very similar to those of the solar system's building blocks is very remarkable, noted Amaya Moro-Martin of the Space Telescope Science Institute. This similarity suggested that the processes forming comets in other star systems might mirror those in our own. The saga of interstellar visitors continued with the discovery of C/2025 N1, also known as ATLAS, or A11PL3Z, on July 2, 2025. Detected by the ATLAS telescope system at Haleakala, Maui, this object was identified by astronomer Larry Denio and an international team as another interstellar comet. Its hyperbolic orbit, with an eccentricity greater than 1.15, confirmed its origins beyond our solar system. Moving at 118,000 miles per hour, C2025 N1 is set to reach perihelion on December 7, 2025, at 160 million miles from the Sun, before exiting toward the constellation Pegasus. Initial observations with the Canada-France-Hawaii telescope and the VLT revealed a faint coma, indicating cometary activity similar to 2I/Borisov. Spectra detected water vapor, cyanogen, and diatomic carbon, suggesting a composition rich in water ices, carbon monoxide, and carbon dioxide, mixed with silicates and organic compounds. Its estimated diameter of 0.6 to 1.2 miles, though some estimates suggest up to 15 miles, makes it comparable to small solar system comets. Unlike Oumuamua, C2025 N1's cometary nature is clear, reinforcing the idea that many interstellar objects are icy bodies ejected from forming planetary systems. The comet's trajectory will bring it closest to Earth on December 2, 2025, at 210 million miles, over twice the Earth-Sun distance, posing no threat. Its closest approach to Mars, at 160 million miles on November 20, 2025, offers a unique opportunity for NASA and ESA orbiters to capture detailed data. As it nears perihelion, its brightness will peak at an apparent magnitude of +12 or +13, visible only through large telescopes. Astronomers are gearing up to study its composition and activity, hoping to unlock further secrets about the chemistry of distant star systems. Why do these interstellar visitors matter? At their core, they are time capsules from other star systems, carrying clues about the formation and evolution of planets far beyond our own. Oumuamua, with its enigmatic shape and lack of cometary activity, challenged our assumptions about celestial bodies. 2I/Borisov, with its familiar cometary traits, suggested that the building blocks of planetary systems are universal. C2025 N1 reinforces this idea, hinting that the molecules essential for life, water, organic compounds, may be common across the galaxy, potentially seeding life on other worlds. These objects also highlight the dynamic nature of the cosmos. Formed in the protoplanetary disks of distant stars, they were likely ejected by gravitational interactions with giant planets, much like the comets in our own Oort cloud. Their journeys, spanning hundreds of millions or even billions of years, offer a window into the violent early histories of planetary systems. By studying their compositions, scientists can piece together the conditions under which other stars and planets formed, shedding light on the prevalence of Earth-like worlds. Moreover, interstellar objects underscore the importance of advanced detection systems. Pan-STARRS, ATLAS, and other telescopes have revolutionized our ability to spot these fleeting visitors. Yet, their transient nature, speeding through our solar system on hyperbolic orbits makes them challenging to study. The European Space Agency's Comet Interceptor, set to launch in 2029, aims to chase and study an interstellar object or long-period comet up close. Similarly, Alan Stern's proposed Interstellar Object Explorer, IOE, could provide unprecedented insights by performing a flyby of an ISO, capturing high-resolution images and spectra. While Oumuamua 2I/Borisov and C-2025 N1 pose no danger to Earth, their discovery raises sobering questions about planetary defense. C-2025 N1, with an estimated diameter of up to 24 kilometers, is twice the size of the meteorite that ended the dinosaur era. Had it been on a collision course, its discovery in July 2025 would have left humanity just 3 months to respond.